Okay.
Okay. All right. So the idea in this problem is you've actually got two ideas here, really, maybe even three. One is entropy.
Mhm.
The second is called enthalpy. And then the third idea here is what's called phase changes. Okay. What if I take it this way? It still looks funky. Can this one? Oh. All right. Go this way. Entropy. Enthalpy. Phase change. Okay, so the idea is this. Imagine that we have an ice cube floating in water.
Mhm.
And let's imagine that the ice cube is melting. Okay. There's two things that are happening when it melts, at least two things. One is heat is flowing into the ice cube from the air and from the water. So there's heat flow. And the symbol that we use for that heat flow, or the concept we use, is called enthalpy. So this is the heat flow. Okay. The other thing that's happening is the molecules, as they melt, as the ice cube molecules melt, which is water, the molecules are become different. They have the same chemical structure, but their arrangements change. Instead of being locked into an ice cube, they're now free to roam around like water molecules.
Mhm.
So they become more disordered as that's occurring. And that idea of order is called entropy. It's actually disorder. And it turns out both of these ideas, the entropy and the enthalpy together, are important when you consider any kind of change that occurs in nature, whether it's a chemical reaction or objects falling apart or things melting or freezing or boiling, all those kinds of physical processes and chemical processes, entropy and enthalpy are important. And so let me turn this on. In my therapy session there. Okay. All right. So we take both of those into account. So here's what so phase change is any time you go from like a liquid to a solid, that would be freezing, or maybe a gas to a liquid, or maybe a solid to a liquid. Any of those things are called phase changes. So because phase changes involve heat flow, either in or out, in this case it's in, and they involve changes in entropy, we can do some analyses based on those three principles. One of the most difficult things to measure directly is entropy. It's just not an easy thing to measure. We can measure heat really well. All you need is a thermometer. And, we can measure temperature really well, thermometer. We can measure pressure pretty well. We've got these little sensors for pressure. Volumes are easy to measure with containers, but it's hard to measure entropy because how do you measure the disorder of something? It's like very difficult to do that. So usually what we do is we measure other things and then figure out the entropy from it. And so here's what happens. Whenever you turn, I'm not going to go through the derivation, but anytime you have a phase change, the change in entropy, I'll call that delta S, is equal to delta H over T. Relatively simple equation. Now, in some textbooks, they'll write it actually directly as heat. They'll say Q for heat over T. But most of the cases we're looking at, because they're at constant pressure, enthalpy change is equal to heat. So we can usually use this one, delta H over T. Okay. So in these problems, usually what they do is they give you delta H. So this is usually given. And then they also give you the temperature. And then you just calculate delta S. And what that will do is it will tell you how much more entropy we have at the end of the process. So if you melt an ice cube, you're forming a liquid. Liquids are more disordered than solids, so you'd have an increase in entropy. Freezing is the opposite. Freezing would be going from a liquid to a solid. That's actually less entropy when you become a solid, so that's a decrease in entropy. So it does depend on the direction. And in thermodynamics, the direction is usually dealt with by using the sign positive or negative. Okay. So I'll talk a little bit about that when we get to the actual calculation, which we're pretty close to doing. Okay. So delta H over T would give you delta S. And the one thing that's complicated about this is usually they don't give you the units in the correct quantity, in the correct units that you need to do the calculation, but that's okay. So what they do is they say they're going to give you delta H here. And it's 28 0.0 kilojoules per mole. And then they tell you the temperature, which is 39.8 degrees C. And then they give you one more piece of information. They give you the mass of dichloromethane. Dichloromethane is CH2Cl2. And the mass is 1.4 grams. So we'll deal with the mass as well. But if you look at the formula, there's no mass in here. So we'll deal with that separately. Okay. So the main thing for figuring out delta S is that you need to know delta H. We know that. You need to know what T is. We know that. That allows you to find delta S. As I said, the units are probably not going to be correct because most chemistry problems assume that you're going to have to do some kind of conversion of units. That's just a common theme, is that anytime you do a calculation, you're going to have to change units at some point. So let me give you a couple pointers here. Entropy is typically joules per kmol. Enthalpy, on the other hand, is typically kilojoules per mole. So that's typically an issue you have to deal with in any of these problems that involve enthalpy and entropy, is that they're going to give you one unit for one of them, but then you've got to find the other unit for the other. You'll have to do some kind of conversion.
Okay.
The other issue that arises whenever we talk about energy is that that temperature cannot be in degrees C. It does not work to do these calculations in degrees C. They need to be in Kelvin.
Okay.
And so the Kelvin temperature is the Celsius temperature plus 273.15. Okay, so you'll need to do both of those conversions. So let's go through it, and then you can sort of see how it works. As I said, you'll notice here that delta H is typically given in kilojoules per mole, but delta S needs to be in joules per mole. So what I would do is I would take the 28.0 kilojoules per mole, and then just multiply it by 1,000 joules per kilojoule. That's the conversion factor. It's 1,000 to 1. So if you put the kilojoules on the bottom, they cancel, and you get 28,000 joules per mole. Okay. The second issue is the temperature. It's in 39.8 degrees C. So you just add 273.15. So that would be 312.95, I think. Yeah, yeah, that sounds right. Okay, so there's your temperature in Kelvin. So once you've got these in those units, you're set to use this formula down there. Okay. You don't need to have the Q. So we can just put 28,000 joules per mole. And then we can divide that by our 312.95 Kelvin. Okay, so I'm gonna bring this up. 28,000 divided by 312.95. And it looks like you got about 89.47. And that's not an unusual number for entropy. Entropy numbers are usually, you know, in the tens or hundreds.
I have a question.
Mm-hmm.
Are my numbers supposed to be different from yours?
Yeah,
Like,
it will always, every time
okay.
it does a problem, it's going to make new numbers.
All right, great. Because I was worried. I was doing it like the way, like,
Mm-hmm.
numbers that was on my screen,
Yeah,
but I
use,
was just making
use
sure.
the numbers you got. Right, exactly.
Okay.
Excellent. Okay, so that's almost the answer. The one kind of little trick they throw into this problem is, again, this idea in chemistry that we always have to do some unit conversions. So the unit conversion here comes into this idea right here. When we do this calculation down here, that's how much entropy change, and you can see it's positive. That's
Mhm.
how much entropy change you get when you have 1 mole. So anytime it says moles down here, that means when you have 1 mole. And in most situations, you don't have 1 mole. Most, you never have like 1 mole of sugar or 1 mole of salt. You have some amount of sugar, maybe 20 grams. You might have 10 grams of salt, but you never have like 1 mole. So the per mole generally has to be converted, given that you'll be given the grams. Okay. So let's go through that. This is actually this last step. It's the next to last step. I misspoke. There's one more thing we'll have to do after this. This next to last step is something that was usually it's covered in Chem 11, but it ends up getting used over and over again. Okay, so here's the idea. We have joule. No, I'm still on eraser. We have joules per kmol. And then they give us 1.4 grams of, they call it dichloromethane, the common name for it is actually methylene chloride. That's what most chemists would call that. They'd say get methylene chloride, but that's okay. It's also dimethyl chloride. So what we want to do is we want to convert this to moles. That's all you gotta do is just convert that to moles. So let's go through it. The way you convert mass to moles is you divide by the molar mass. So whenever you have the mass, the moles will be a smaller number because the molar mass is always greater than 1. So if you're dividing by a number greater than 1, you're going to get a smaller number. So we just have to figure out what the molar mass is. So carbon is 12.01. There's 2 hydrogens, each one's 1.01. And then there's 2 chlorines. I'll do that. 2 times 35.45. So let's see, that's 70.9, 72.9, 84.93. Yeah, grams per mole. So that's your molar mass. So you take your mass and you divide by the molar mass. And that'll give you the number of moles. So 1.4 divided by 84.93 is 0.016. It's a small number. Like I said, when you divide by the molar mass, you can get a smaller number. 0.01648 moles. Okay. Now we're almost there. We just have one more step to do. When it's per mole and you want to, and you're given the mass, you know, the one thing I'd say about this problem that's a little bit challenging is they don't tell you what units to be in, although they may when you see the box over to the right, where you enter the answer, they may have the units next to it. I'm not sure. I can't see it on my screen, but maybe they do that. So let me make some space here. So the way, this is sometimes people have a problem with this. The way you deal with this is you take that number that we got over here. And you just multiply it by the number of moles. And what happens is the moles cancel. And so then you just got joules per Kelvin. So if they tell you in the answer that the units are joules per Kelvin, you would know, now you would know why that works out. So times 89.47. So now it's going to be even smaller, 1.47, and they want it to 2 significant digits. So I'm just going to round it to 2 significant digits, 1.5. And then that would be joules per Kelvin. It's going to be a small number because if you had 1 mole would weigh 84.93 grams. That's how much 1 mole weighs. We don't have anywhere near that. We only have 1.4 grams. That's not even close to 84.93 grams. So, you know, it's sort of like mileage in a car. If I say you can drive 30 miles per gallon, but then I tell you I'm only going to give you like, you know, 0.1 gallons, you can't drive 30 miles on 0.1 gallons. So you can only drive about 3 miles on 0.1 gallons. So it'll be a much smaller number. And the last thing you want to do for this problem is the sign. So the way the sign works is I would just reason through it. Anytime something goes to a solid, that's a decrease in entropy, it's negative. Anytime something goes to a liquid from a gas, that's less entropy, that's a negative. If something goes from solid to liquid or solid to gas, that's an increase in entropy, so that would be positive. Okay, so I'll write a little box here. This is the way I think of it. Solid, lower entropy. Liquid, in between entropy. And then gas, come on, now. And then gas. This has high entropy. So when someone says condenses, what they mean is it's going from a liquid to a solid. That's condensing. Okay. So if it's condensing, it's going to lower entropy. So that would be a negative.
Okay.
Anytime you're going to a lower, that's negative. So downward is negative. Going up is positive. Okay. So this says that if we condensed, in other words, we took a certain amount of liquid, dichloromethane, 1.4 grams, and we condensed it into a solid. Actually, it's talking about going from a gas to a liquid, but it doesn't matter. Then it would be a decrease in entropy by 1.5 joules per Kelvin. Okay. So do you want the one that came up on your screen free? You want to try that one now?
I think I could try it on my own. I started doing most of it. All I have to do is find the molar mass per element, and I think I pretty much got it. I do understand this. Like, you're making it really like clear for me to understand.
It's a very specific type of problem. It's not like a general problem that most people deal with. It's very specific. But it is relatively simple. It's just that with this one, the devil's in the details. Like all these unit conversions you have to get.
Yeah.
The sign you have to get. That's where most people are going to make their mistakes. The general formula is very simple. Delta S is just delta H over T. So you just got to take one over the other, but you're going to have to get all these units right and stuff. So,
Okay.
like I said, I'm recording this and then I'll send you a link to the video.
Yes, please.
And then, as you're going through, if you start running into problems on it, you can refer back and, get those details just right. Okay. All right. So let's look at the next one.
This one.
The next one should be, well, that's a good question. I don't know what the next one. Are you able to tell what it would be for you?
It tells me predicting qualitative how entropy changes with temperature and volume.
Excellent. Okay. Let's bring this one up. Okay. Now this one is, I think, one of the easier ones because it's just a very conceptual thing and you just have to kind of ignore the information that's unimportant. Okay. So let's take a look at it. Of course, it says qualitatively, so that means you don't have to worry about doing a calculation on it. You're just saying whether something's getting bigger or smaller or not changing enough. That's all you're doing. So for each system listed in the first column, so that's over here, decide if it's possible, because sometimes it's not possible to tell, whether the change described in the second column will increase the entropy S of the system, decrease entropy S, or leave it unchanged. If you don't have enough information to decide, just check the not enough information in the last column. Okay. So the idea here is relatively simple. If something gets hotter, it will become more disordered. And we see this in nature all the time. In biology, it's really, really apparent. So it turns out that all these microorganisms that sometimes attack our bodies are tuned to be effective at the temperature of our bodies, which is 37 degrees Celsius. So if your body senses that there's an infection that it needs to fight off, one of the defenses is to raise the temperature. The body actually has the ability to raise the temperature by metabolizing glucose more rapidly and by shutting down the ability to release heat, through sweating and actually you can shiver. Shiver's another way to produce more, to create more heat within our bodies. And what'll happen is the proteins, like all these microorganisms that can attack us, they're very dependent on the structures of these proteins that can stick to the surface of our cells in order to infect them. So what happens is by raising the temperature, these proteins that these microorganisms use, their shapes change a little bit. Not a whole lot, but enough that they can't work as well. They're less effective at attaching. And so what that tells us is that temperature is highly related or highly connected to shapes of proteins. And the shape of a protein is so essential to how well it works that by changing the shape even slightly, it cannot work anymore. It might not work at all. It might work less effectively or maybe not even at all. The shape of a protein is interesting. People study it. They put a lot of effort into figuring out the shapes of these. And it turns out the shape of a protein is highly connected to how much entropy it has, the disorder that it has. So if I take a protein and I just put it out as a string, it has a different amount of entropy than it has if it's all folded up as its regular way. And if I unfold it slightly and make it more random and less effective, that changes the amount of entropy that it has as well. So in general, what we see is that more temperature is more entropy. The disorder goes up with temperature. And the limit of that, the extreme limit, would be 0 Kelvin. If you could bring something down to 0 Kelvin, it would essentially be perfectly ordered. It would have no entropy at all. Now, it turns out that's impossible. We can't actually come down exactly to 0 Kelvin, but you can get pretty close. And we can observe that crystals have very little entropy at very low temperatures. So as the temperature goes up, entropy goes up. And that's really all you got to remember. Temperature goes up, entropy goes up. Similarly with volume, if you imagine, for example, taking a child and giving them 1 million toys and then giving them an entire house and time, those toys could be strewn about the entire house. And that would be more disordered than if you just gave them one room. If it was just one room, they could create disorder in that room, but they couldn't create disorder in the other rooms. So in general, as volume goes up, entropy goes up as well. And so you can just remember it this way: temperature goes up, entropy goes up, volume goes up, entropy goes up. And that's true for children and people, but it's also true for molecules. Molecules, as they expand into bigger volumes, they become more disordered. As they get hotter, they vibrate and they move around more, they're more disordered. So let's take a look at these. There's 3 of them here. A few moles of nitrogen gas, so just a sample gas. It's cooled. So notice it got colder. And then it says the volume is held constant. So that's a way of telling us, don't worry about the volume. It's not changing. So the volume is not affecting this. It's just getting colder. So colder is a lower temperature, so entropy goes down. And the way we write that mathematically, when something gets smaller, decreases, the change, remember the delta means change, the change in entropy is less than 0. It's a negative number, meaning it got smaller. So for this one, we would select the less than 0 sign. Okay. Second one, again, it's a gas. You got a few moles of carbon dioxide gas. It's heated, getting hotter, temperature's going up. Then it says the volume's getting smaller. So the volume's going down. So notice those are 2 contradictory things, right? Temperature's going up, so more entropy, but volume's going down, so less entropy. Can't really tell. You don't really know. Technically, that would be enough information to answer the question, but not for this course. We're not going to have you do these change in temperature, change in volume calculations of entropy. If this was a chemistry majors course and you were a junior in chemistry, we'd have you do that calculation. But we don't expect you to do that here. So if you get contradictory information, temperature goes up, but volume goes down, then you can just say, look, we don't know. It's just not enough information.
Okay.
Okay. If they both went up, then that's additive and we would know that it increased. If they both went down, then that's additive and we would know that's a decrease. But if they're contradictory, then you can't tell. The third one is, again, now this is liquid, but notice it's getting heated and nothing about volume, right? It went from colder to hotter. So if it gets hotter, that's an increase in temperature. So that would be an increase in entropy. That would be greater than 0. All right. Does that make sense?
Yes.
Yeah, those ones are pretty fun once you've done a couple of them. And again, sometimes they'll have some information in there that you don't really need, but you know, this one was the easiest one right here because it didn't have any other information. This one, you know, it's what's interesting. The first one and third one, the first and the third are the same, really. Well, yeah, I would say they're this. Well, actually, now that I'm thinking about it, the third one, I'm not convinced that I'm right about that because it said it was heated, but it didn't say anything about the volume. I would assume the volume didn't change, but it's possible it did, and they just didn't tell us. So I'm going to check on that just to make sure. My assumption would be that if there's no information about the volume, we'll assume it didn't change. So it should be greater than 0. But let me check. They might say it's not enough information. Okay, so they agreed with me. They said, yeah, the temperature went up, so that's a greater than 0. Okay. Technically, in a way, they may be wrong and I may be wrong because we don't really know what happened to the volume, but they're saying don't worry about that. So that's fine. Okay. I think that's probably pretty straightforward, you. So let's look at the one that comes right after that one. It's very similar. The difference is instead of, oops, screwed up. Instead of how it changes with temperature and volume, the next one is it's how it changes with mixing and separating. So let me bring that up because that almost always comes up right after the temperature volume one. And if you look at it, you'll see it looks like a very similar type of problem. The difference here, again, is qualitative. The difference is what happens when you're mixing or separating. Okay. So for each system listed in the first column of the table below, decide if it's possible whether the change described in the second column will increase entropy of the system, decrease it, or leave it unchanged. If you don't have enough information to decide, check the not enough information. And for advanced students, you can assume that it's ideal gas law behavior. Okay. So this is the idea of mixing things and separating things. And so this is also very simple. Mixing creates more entropy, more disorder. If you mix things, they're just more random, so it's more disorder. You know, like that, there was old commercials for Ivory soap that it was 99.99 something % pure. When things are pure, there's more order, less disorder. So anytime you add anything together, you create more disorder. Okay. So there's words that are used in here: osmosis, reverse osmosis, filtration, but the principle is always the same. If you're mixing things together, you'll have more entropy. Delta S will be positive. If you're separating things, that will be less entropy, less disorder. So the first one, a liter of seawater is at 15 degrees Celsius. The water is passed through a reverse osmosis filter. which separates it into 750 milliliters of pure water, 250 milliliters of brine, which is very salty water. You're separating things. The water is now pure. Separation creates less entropy. So that would be less than 0. Okay. You don't have to worry about how much is in there. You don't have to worry about the details of how it was done. The point is, if you separate things, you have less entropy. The second one, 20 liters of pure carbon dioxide, 20 liters of pure oxygen, both at 5 atmospheres and 19 degrees Celsius. They're mixed. You're mixing these gases together. Pressure is kept constant at 5 atmospheres. Again, the pressure is unimportant for our purposes. We don't need to know anything about that. We don't need to know how much. We just need to know that they were mixed. Whenever you mix things together, that increases entropy. Almost as if you took cards, 2 decks of cards, and shuffled them together. That creates more randomness, more entropy. So again, if you are mixing things together, that would be an increase in entropy, so it'd be greater than 0. The last one, a gram of ammonium bromide, which is NH4Br, 2 liters of pure water, which is 78 degrees Celsius. We're going to dissolve it, right? Dissolving is the same thing as mixing, right? We're taking a solid, adding it to a liquid. That's mixing. Mixing, again, is an increase in entropy, so that would be greater than 0. Okay. How do you feel about that one?
I get it.
Yeah. Pretty simple, right?
Yeah.
It's kind of cool. So, I mean, that's in a way, that's how chemists think about entropy. Does it create more? Does it create less? So if you go on to take organic chemistry, they actually talk about like reactions from that perspective. Oh, that reaction created more entropy. So that's going to be a reason why the reaction occurs, because in general, more entropy is associated with reactions occurring versus not occurring. So they tend to happen faster if there's more entropy. And actually, you think about it, like reverse filtration, reverse osmosis, that's usually a very slow process. Separating things is usually slower than mixing them together. If you've ever cleaned a room, it's easier to mess up a room than it is to clean the room, to create order.
Yep.
It's sort of the nature. Okay, so that's those two. There's one more that's also similar, I think. Yeah, this one right here. And this one is sort of the pinnacle of this. This is what brings it into chemistry. Oh, I think so let's bring this. These three I usually associate as being similar. So this is, again, qualitatively predicting but now we're going to call it the reaction entropy. So now we're doing chemistry. Mixing things together is chemistry, but those are physical processes. Increasing the temperature, increasing the volume, those are physical processes. There's no real chemical change occurring. Atoms are not rearranging at the atomic level, at the molecular level. Now we're going to talk about actual chemical reactions. What happens when we have chemical reactions? Similar idea. There's a couple of very basic principles. One of which is that if you produce gas molecules, I'm going to say net gas molecules, meaning you have more gas molecules at the end than you have at the beginning, that tends to increase entropy. Delta S would be greater than 0. So more gases at the end, more entropy. The opposite is true too. If you decrease the amount of gases, that tends to be a decrease in entropy. Whenever you change things to pure, actually, that doesn't really pertain in this one because I don't see any where that happens. So anytime you go from a gas to a solid or a gas to a liquid, that's a decrease in entropy. Gases have the most entropy. They're the most random. So anytime you produce a gas from a solid or a liquid, that's more entropy. Anytime you produce a solid or a liquid from a gas, that's less entropy. So let's take a look and see if those principles work. The first one, everything's a gas. 2C2H6, gas. 7O2, gas. 4CO2, gas. 6H2O, gas. All gases. So what you do next is you count up how many. On the reactant side, there's a total of 9 gases, right? You have 2 plus 7, that's 9 molecules of gases. On the product side, you got 4 plus 6, that's 10. So it's not a big difference. It's only a 10% difference, but you do have more gases at the end. So more gas, more entropy. So it would be greater than 0. Okay. Second one. Here there are no gases at all. We have aqueous, aqueous, solid, and aqueous. Now, remember, aqueous, we call that a state of matter, but it's really a mixture. Aqueous really means you've got water and something in the water. If we just have water, we call it a liquid. So aqueous is actually a mixture. So here we have a mixture and a mixture. Now we have a solid and a mixture. So again, you still have a mixture here, but you have a solid. So anytime you go from a mixture to a pure substance, aqueous cannot be pure because it's 2 substances at least. But solids, liquids, and gases can be pure. So anytime you go from an aqueous, which is a mixture, to a solid or a liquid, that would be a decrease in entropy. Okay? So you can essentially say this aqueous cancels that aqueous approximately. Aqueous goes to solid. Solid is less entropy. So that would be a decrease in entropy. Okay? The last one. Solid, gas, solid, liquid. So again, you could probably say, look, the solid cancels the solid. They both have about the same amount of entropy. And again, this is just a qualitative assessment. We're not doing the actual numbers. But look what we have here. We have 2 gases turning to 2 liquids. So that's a loss of gas. Anytime you lose gas, that's a decrease in entropy. If it had been the reverse, if the liquid had turned into gas, that would be more entropy, but we have a gas turning into a liquid, so that's less entropy. So that would be less than 0. Okay. Any questions on that one?
No.
Yeah, those 3 are pretty good, right? Those 3 are pretty straightforward.
Yeah.
They're conceptual, but they're important concepts. So if you know how to do those, that's really good. So there's that one. So what I'm going to do. Oh, let's look at this one. So this one again, it's a qualitative idea. I actually put a bunch of qualitative ones in there so that you can kind of get the concepts. This one's similar. It's a little bit different, but this one's going to take 2 ideas though. So in a way, this is related to the first problem we did where we had the phase change, where we went from like a gas to a liquid. And this one goes a little bit further. It actually says, is the reaction spontaneous or not? So let me just talk about it for a moment, because this one has a couple of important concepts. And I didn't have you guys do a lot of calculations on these problems, but this one sets you up to do calculations. So here's the idea. When we say entropy, what's really, one of the things that's really powerful about entropy is we can use it to make predictions. It turns out that if we wanted to predict whether a rock falls down a hill or falls up a hill, we can use entropy to answer that question. Sometimes entropy is called the arrow of time. Because if we calculate entropy, we can actually use it to predict what will happen. So if you were to watch a movie and you saw this rock fall up into a man's hand, went up, you would know that they're running the video backwards. You would just know that intuitively. So the reason that the rock doesn't fall up, rocks don't fall up, and they do fall down, is because of entropy. At least that's one reason they do. Anything that increases entropy we call it a spontaneous process. And in practice, spontaneous means essentially it happens. Technically, it means you don't have to put energy to make it happen, but intuitively, it just means it happens. So if you put an ice cube in water and it's hot outside, you know that ice cube's eventually going to melt. That's a spontaneous process. If it's hot outside and you put an ice cube in the water, the ice cube's not going to freeze the water. That's not going to happen. You know that. That's just not a spontaneous process. On the other hand, if it's really cold outside and you pour some liquid water, you know it'll freeze, right? So spontaneity, whether something happens without an input of energy, it's intimately connected to entropy. If you increase entropy in a process, that's a spontaneous process. So here's how we deal with this. We call that entropy change the universe. So the total, you could think of it as total or universe. And that change in entropy of the universe is equal to the change in entropy of what we call the system, plus the change in entropy of the surroundings. Okay? What we've been doing qualitatively, melting, does that increase the entropy? Temperature increase, does that increase the entropy? All those things, that's the system we've been doing. We've been evaluating that. If something melts, it's a liquid, it has more entropy than it does as a solid. If the temperature is higher, it has more entropy. We've been doing that already. The surroundings is a little bit different. The surroundings is connected actually to heat. If heat goes in, we call that endothermic. And we say that delta H is positive, greater than 0. Okay? If something is endothermic, delta S of the surroundings is less than 0. Here's the key. So if something is endothermic or heat goes in, you just want to remember delta S of the surroundings is less than 0. If heat goes out, we call that exothermic. Then delta H is less than 0, and delta S of the surroundings is greater than 0. Okay. Now here's the result of that. I'm going to rewrite this equation. If this is positive and this is positive, then this has to be positive, right? Adding two positive numbers gives you a positive. If this is negative and this is negative, then this has to be negative also. Adding two negatives gives you a negative. However, if this is positive and this is negative, then we can't really know for sure what happens to that one, unless we have more information. And if this one is negative and this one is positive, same thing. We don't really know what that is unless we have more information. Okay. So there are ways to get more information. We may need to do it for this problem, but if So let me write it here. Did I write it over here? I didn't. So if delta S of the universe is greater than 0, that's spontaneous. And if delta S of the universe is less than 0, that's not spontaneous. Okay, so there's just a lot of things you have to remember here.
Okay.
First thing I would remember is delta S of the universe. If it's greater than 0, that's spontaneous. If it's less than 0, that's non-spontaneous. Then the next thing I would remember is that, I would just write this table down and have that table available. If this is positive and that's positive, that's gonna be positive. If these are both negative, it'll be negative. If they're opposite signs, you don't really know unless you get more information. And then that should be enough for you to figure out some of them. They may actually give you ones, I have to look at them. They may give you ones where they say it's spontaneous below some temperature or above some temperature. If we have to do that, then we'll deal with that separately. But what I would say is, for 2 of them, for 2 of them, you don't know. So let me take a look. Okay. Looks like we don't need to go any deeper than that. Looks like that's enough. So let's take a look at it. Oh, I have to stop share. Okay, so here we go. So read the descriptions of the physical or chemical changes in the table below, then decide whether the change will be spontaneous. If you can, you may not be able to. Okay, so let's take a look at the first one. The first one says a gas condenses to a liquid. Okay, so that's delta S of the system. When you go from a gas to a liquid, that's a decrease in entropy. So that's a negative sign. Mm-hmm. Then it says you release heat. Releasing heat, delta H is negative, but delta S of the surroundings is positive. So if delta S of the surroundings is positive for the second part, but negative for the first part, you can't tell. They're opposite signs, right? So you just can't decide with that information. Exothermic. Oh, delta H is negative, so delta S of the surroundings is positive. So we have one positive. It's a reaction between a solid and a liquid that gives you gases, forming gases. That's a positive, right? Mm-hmm. 2 positives added together is a positive. So the answer is we got positive, so that's spontaneous. Yes. Okay. See how it works? Mm-hmm. You get a positive is spontaneous, negative, not spontaneous. Can't tell if it's positive or negative. You don't know. Third one, endothermic. Delta H is positive, so delta S is negative. So we have a negative there. Liquids gives us gases. Oh, liquid gives us, that's a positive. Whenever you get more gases, that's a positive. So we have a negative and a positive. Contradictory, cannot tell. So for that one, we can't decide with the information. Okay. And there you go. So a little bit different, but a little bit more involved, right? There's 2 things you're having to deal with here for spontaneity. It is one of the biggest challenges for students, for anyone really, is that we can't tell whether something is spontaneous from one of the 2 entropies. So if we only know whether it went from a liquid to a gas, that doesn't tell us. If it's endothermic or exothermic, that can't tell us. But the 2 together can tell us. And that's what this one is getting at. That you have to do both of them, figure out if it's positive, negative, or can't tell. Okay? All right, that's good. We made very good progress. We did like 5 problems, which is pretty good. So when I'm going to stop sharing here, and then I'm going to stop the recording.